Can you see the screen?
Yes, we can see it.
Okay, yes. So what we will be doing today is involution and Desargues theorems. So I shall begin by defining what a projective map is. So a projective map is what we call so F is defined from some S1 to S2. S1 and S2 can either be like it can either be a line, conic, or a pencil of lines. And F preserves cross ratios. Yeah, so that's the definition of a projective map. Uh, One more thing to note is that F, since projective maps are bijective, so F has to be bijective. Oh, we are working in RP square, by the way. Just to know. So like we are always working in RP square today at least. So F is bijective. Also, like there is a general statement that if you see some bijective map, it is probably projective. That is not mathematically correct, but what they actually mean to say is that if you see some bijective map which appears naturally, there's a good chance that it is projective. So also the composition of projective maps is projective. Basically, if F comma G are projective, then F composite G is also projective. Okay, can anyone give some examples of projective maps that you know already?
Inversion.
Yes. Okay. Okay. We'll come back to inversion. Let's start with the basic
Homothety.
translation.
Translation.
Yes. Homothety is a good example. So homothety. What is this? Okay.
Translation and reflection.
Sorry.
Translation and reflection.
Yeah. True. Okay. Reflection about the line you mean, or
Yeah,
what?
about the line.
Yeah. True. So
Or
homothety translation.
reflection in a point.
That is homothety with Trishul.
Acha, haan. We can also do rotations.
Yeah. Yeah. We can write that. Homothety translation rotation.
And
Wait, it's the other
similarity.
one you said. Reflection, etc. So these are the standard ones. So these preserve cross ratios. Actually, this preserve ratios as such. So uh, these make sense. Yeah, that is right. Another things that you know is that what you do while projecting. Like if you have two lines,
Perspectivity.
yes, exactly. So if you have two lines, you can project from a point. So you can project from this point. So this map is bijective, it is projective. Similarly, okay, so if when basically you are doing this, you are basically projecting from this line, like to this pencil of lines. So that's one projective map, and from this pencil of lines, you are projecting onto this line. So that is basically a composition of projective maps if you observe. So similarly, you have a conic, and you have a point on the conic. You have a line there you can project, and you can also project from a conic to itself. Okay, so these are the standard projective maps that you might have known. One more thing, okay, as now Mandar said, inversion is projective. That is true. So inversion is projective. Just one thing to note here is inversion in a plane is not projective. Inversion that swaps to clients or to entities is projective, but inversion in a plane is not projective. Like what I mean to say is that if an inversion swaps this circle and this line, let's say, then it is projective. It is projective on these two. Like if you have like a comma b, c comma d is equal to. So this holds, but inversion as a thing in the plane is not projective. Just because if you observe in the point at like when you invert about a circle, you don't know which point at infinity the center goes to, right? I mean, it goes to some point at infinity, but you don't know which point at infinity, like along which line. But here you know that the center will go along point at infinity or along this line. Does that make sense?
Yeah.
Yeah. Okay. Okay. Feel free to ask me any questions anytime or like interrupt. Okay, if that makes sense to everyone, I'll go ahead. So these are the some standard projective maps that we know. Okay, so now we will come to the first main thing that we will be studying today, that is involutions. Involutions and basically involution pairs also. So for what is an involution? So F is defined from S to S, where S is again like line, conic, or pencil. So F preserves cross ratio. These are the conditions where we call F to be an involution. F composite F is the identity, and of course F is not identity. These are the things for which then F is said to be an involution.
Wait, what's the meaning of the point F composite of F is equal to an identity?
Okay, so F composite F is like F of X, or like F of P, let's say, is same as point P.
Okay, yes. Bijective.
This is an involution, like F has to be bijective for this to occur, not the other way around.
Okay, fine.
Yeah, so this obviously implies F is bijective, that you said is correct. So this is a projective map from a line, conic, or pencil to itself. Okay. Now we will start and okay. And so if f swaps a and b, like f of a is equal to b, so and f of b equal to a, because f is an evolution, then we say a comma b is an evolution pair in f. Does that make sense? Because this is symmetric. F of a is b and f of b is a. Yeah. So this is what we mean. Okay, now we will study involution based on a line. So if you have some line, basically we will classify involutions on the line. So you can show that so this is the line L and this is P infinity. So if F refined from L to L is involution, then F is an inversion about some point in L. Can someone try to explain like why this should be true?
Wait, so what is the thing?
Okay, so if you have I have a line L and you have some function f different from L to L, which is an involution. So
L12
basically,
means lines alone.
what?
It just swaps lines with lines, correct? This
Oh, F
function.
different from L to L is like f is different from points of L to points on L.
Okay, on the same line. Okay.
Yeah, on the same line. So what we want to show is that basically you have some point P and then f is just inversion about P. Like you have some P and radius R, let's say, so that if x comma y are involution pairs, then Px into Py equal to R square. Inversion can be negative as well, or it can also be like reflection about a line, maybe reflection about a point, I should say. Like it can also be reflection about a point, but then we can just say that it's a reflection in this line, which is in the circle with center at point and infinity. So that we can classify it that way. So it is either a reflection about a point or inversion, possibly negative. Can anyone outline the proof? I will not be doing all the cross associates basically, but we can probably outline the proof of how it should work. Okay, I will outline some part of it. So we say that let P comma infinity be an involution pair under F. Then let's say x1 comma x2 and y1 comma y2 are two other involution pairs. Then you chase and show basically that px1 into px2 is equal to py1 sorry, py1 into py2. So basically show that this thing is constant and hence it's just inversion about p. On the other hand, if p is not a real point, p is the point at infinity again, like infinity comma infinity is the involution pair, then you show that it has to be a homotheity with some ratio k and some point. And since it is an involution, you get k square equal to 1. So k has to be plus minus 1. But plus 1 will give you identity, so you discard that and you get k equal to minus 1, reflection about some. Is that fine?
Yeah.
Okay. Should I proceed? Is it fine with everyone? Because okay. If anyone has any doubt, you can just ask. So I will proceed. So now we have, if you saw inversion on a line, so inversion on a line is basically inversion, possibly negative, about some point, real point, or it can, or it is like reflection about. Right. Okay. So now, okay. What is the involution? Like, you can't really classify involutions of the pencil of line, but what we mean by that is basically, if we, this is a pencil of lines, and F is an involution. Then what you basically get is that if you project this on any other line, like this is some point P through which we are fitting the pencil, and this is some other line L, then if you project from P onto the line L, the resulting function will also be a involution. That is involution about pencil of lines. Also, it generally doesn't matter what L you take, that's due to perspectivity. And one additional thing is that okay, yes. So some involutions on pencil of lines can be it's like rotation by 90 degrees. These are not exclusively all the involutions, but some which recurring, let's say recurring involutions, recurring patterns, or which you might observe many times. It's either rotation by 90 degrees or reflection about some point, reflection about a line, about some line in the pencil of lines. So these are not, and etc. etc. Like I just write. I mean, there are many more. I mean, of course, there are many more, but these are some of the recurring things which we might get. Okay, so we'll now get to the inversion on a conic. Inversion on a conic is pretty interesting. Okay, for inversion on a conic, what you have is that it is always with respect to some point P, you have things like A comma B, B comma D, and if you have some tangent, let's say K comma K, things like this. Like you are just projecting from P onto the conic again. That is an inversion on a conic. Can someone try to prove this? Maybe not actual proof, but like outline the proof.
Maybe we'll want to prove that tangents go to themselves, tangency points go to themselves.
No, thing is that point P is not fixed, right? I mean, what I'm trying to say is that if you're given some, like if you're given some f from C to C, which is an involution, then there exists point P such that this thing happens, such that f is like projection from P onto itself, or
Correct. So that
projection
means
from
that
C.
there's 2 points which map to themselves, right?
Yeah, sure. Wait, how do you show that?
Because if it was true, if the statement was true, then the tangency points will have to map to themselves because of the
Yeah,
projection. So you have to prove it. Let me think 1 minute.
yeah. Maybe try to use what we have already shown before. Even that can.
My Wi-Fi was a bit bad, so I couldn't hear. What are we doing?
Till which part did you put it there?
I didn't hear anything of involution on opponent.
Okay. So inversion on a conic, we are trying to show that there exists some point through which you are projecting on the conic itself. That's how you can classify all the involutions.
Okay, so if you want to show that if A and B and C and D are pairs, then everything is like, if their intersection is P, then everything is being projected from P.
Yeah.
Wait, are all involutions of this type continuous on anything, not just phoning?
Okay, this should be continuous because now we know that you can classify all such things like this. But I don't think you can like start by assuming they are continuous. I'm not really sure if you can do that. Maybe you can prove it somehow due to cross ratios, but I'm not sure. Okay, one thing I should have mentioned at the start probably is that um wait, I'll mention it down. Maybe it can be used. So one interesting thing is that projective maps.
Okay, I think I got the two.
Yes, go.
Okay, so say you want to show that f of x is equal to ex cap the conic. So
Mhm.
we have x. So now the cross ratio A, B, X, C after projecting from F becomes BA f of x D,
Yeah.
which is equal to ABXC. But now the thing is ABXC is also equal to B Y BAYD, where Y is PX cap the conic. But since you can easily see that cross ratios, if they're equal, then they have to be the same point. We immediately get that f of x should be the intersection.
Yeah, that makes sense. So what he means to say is you have x and y, for example. Like let's say xy is some inversion pair. Let px cap conic be some x dash. Then like if xy are x and y is an involution
So we
pair, some
do
involution.
basically a phantom point. Like we show that the cross ratio of x prime is equal to y. So then we get that x
Yeah,
prime to y.
Yes, makes sense. So you have that A, B, C, X is equal to P, A, D, Y. But by projecting from P, we also know that this is equal to B, A, B, A, B, A, D, X dash. So you get that X dash is same as Y.
Wait, while projecting from BADY, what are we projecting through?
B, A, D, Y. Oh, this is
Through
the,
what?
this is projecting from P, and
Yes,
this
done.
is the using F results cross section.
Oh,
Oh wait, it's opposite, sorry. Here you are projecting from P, and here you use F results cross section.
oh yes, okay.
Yeah, so here this is FF, and here you are projecting from P. Is that clear to everyone?
Yes.
Okay. So interesting thing about involutions is that they are preserved under projective maps. So projective maps preserve involutions. So if you, for example, if you have something like F is different from, let's say, L to L, like, my bad. L to L is a involution. And G is different from L to, let's say, some conic C or something, is a projective map. Then H is different from C to C, and H we define as what? Yeah, the G of, yep, sorry,
GFG inverse.
yeah, exactly. GFJ inverse of whatever. So H is basically is an involution. This isn't too hard to show by just the bijectivity of F and G, and F is an involution. So basically, G inverse exists because G is a projective map and they are always bijective. So you get that this is also an involution. Just to clarify what I mean is that if you have some line and let's say you have some conic. Okay, wherever I'm using conic, like we can, like almost always in like olympiad geometry, we will use circles, but I'll just say conic too because conics are more general. So if you have, let's say, A, B, C, D, and you, okay, it doesn't draw nicely, but it's fine. And you have somehow you have E and F also, such that A comma B, C comma D, and E comma F are involution pairs in some, what happened? Are involution pairs in some function on line L. Then by projecting from point P, you will get that A dash comma B dash, C dash comma D dash, and E dash comma F dash are involution pairs on some function G on conic C. Is that clear? What I mean by involutions are preserved under projective maps?
Yes. So actually, then this means that if we know for a line, and then we can project the line onto a conic, then can't we just find the involutions of the conic from the involutions of the line like this?
Yes, exactly. That is what I was getting to. So can you, I mean, we can maybe. So if you have what we wanted to show here, that the inversion on a conic can be classified like this, can also be proved that way. So what we do is you have a conic. Basically, you can just like okay, for simplicity, we will just assume it's a circle for now. I mean, we can do it otherwise, but still. If it's a circle, what you can do is you can just invert about some point on the circle. So that would make this go to a line through the point. And since this inversion swaps these two, swap the circle and the line, what you will get is involution pairs are preserved. And we have already classified involution pairs on the line as some inversion. And then you invert back to get that all the inversion pairs are such that they concur at one point. Does that make sense? And as Gaurav said, like if you have a general conic, you can also choose a point on the you can choose a point on the thing, project to a line, get that these are inversion pairs of some inversion, project it back, and show that they concur at a point. Does that make sense?
Yes.
Okay.
What else can we apply this sort of technique to and get?
Sorry, what do you mean? I did not get it.
As in, can we apply this technique to anything else and get the involutions?
Anything else such as?
No, as in something where we can apply this technique and then get it's basically the same as the involutions of the line.
Okay. Basically, for some other thing, you are trying to classify the involutions by transforming like it into a line. I mean, transforming by me projecting it to a line.
Yes.
Okay, interesting. I have not thought about this as yet. You might somehow be able to classify the involutions on a pencil as well. I have not done that. But like it will probably require some weird angle condition, like the sines of those angles by ratio lemma. But I think you might be able to, like if you have a pencil of lines, you take something, then you show these are involution pairs. So you just take some a point here and this line maybe, then you can like maybe translate everything in terms of sines of these angles. I am not sure. Maybe you can.
But is there anything else we can have a projective transformation from the line into other than a ellipse? No, as in any conic.
Oh, I am not sure. Projective transformation to a line, I mean projective map to a line from a conic or a pencil. That's what I know. I am not really. What do you mean from a conic or not from a conic?
As in, yes, actually they preserve conics, don't they? Yes.
Yeah, exactly.
Ah, okay, thank you.
Okay, so this is what we were doing. Okay, so in olympiad geometry, how can you use involution somehow? Is like you have some line and you want to show that there exists x such that xa into xp equal to xa into xt. This helps in power of point things. This way you can use in classification of involutions, or this helps in using or proving concurrency of chords. Also, you can prove this to show isogonal maybe lines or something. We will see examples like this after we discuss DIT and DDIT. Okay, yeah. So, okay, are we going? Okay, so we will now discuss DIT. Is everything clear to everyone until now, or should I repeat anything?
I was a bit lost in the last point, the last thing you mentioned.
Which thing?
You said power of point. So you said how to prove this, right? I didn't understand how. Can you?
No, I was just saying like you can use it to, like if you have something like A comma B, C comma D, and E comma F are involutions pairs.
Yes.
Then you will get that there exists point x such that xa into xb equal to xc into xg is equal to xc into xf. Oh, sorry.
For any
On any line, right?
project,
Because we
on any
classify
line,
the
only a
involution
line.
equation line.
Okay. Only for
And
line.
like, yeah, and you can like somehow you might condition some other condition on this, you will get this equal to something else and use the power of point.
Okay. Yes.
This part was like for using or proving concurrency of chords. Like somehow in a circle, you are given that these chords are concurrent, but you don't really know how to use that condition. You might translate that into involutions and project from some point.
Okay. I see. But how do you use it for isogonal lines?
Okay, so what you can do is we'll come back to this later, but I'll just still say
Yes.
what you can do. So if you have something like this, maybe you have some 6 lines, you somehow show that yeah, you have this involution pairs.
Okay. Yes. Fine.
And you want to show that AF and AG are isogonal in angle BSE, and you know that these are isogonal and these are obviously isogonal. So if you get this thing, since these two involutions satisfy that they are reflection about angle bisecting.
Okay. So the other inversion. Yes. Okay.
Yeah. Okay, I should have mentioned this. Let me mention this now. Uh, sorry. Okay, how many involutions do you think, how many involution pairs do you think we require to uniquely determine an involution function?
Two.
Yes, 2 is correct. Can you elaborate why?
Yeah, so like involution is essentially it is like an inversion or one of the other stuff you stated. So when you get two pairs, you can actually find the radius of inversion, and then it's fixed because the center is just the map of infinity.
Yeah, exactly. So like if you see what Atharva's proved it, wait, what is that? Yeah, so he took these chords A, B, and C, D, and then he intersected at P. So if you get two pairs of involution, the involution gets uniquely determined. And you can also get, and you can also choose like without orthogonality any two inversion pairs. Also like you can choose something like A comma A and B comma C or something. Like A comma A basically means that f of A is A. So this is indeed possible. Also, one more thing you can show that since f preserves cross ratio, so if A comma B and C comma D are involution pairs, and for any other point P, you have that A B P C, let's say, is equal to B A f of P D. So f of P is uniquely determined using only these two, right? Is this clear or should I repeat? Okay, any doubts specifically?
No.
Okay, nice. So we will proceed. So we got that two involution pairs. Uniquely determine and uniquely is important. And that is why if you have like here, so ABAC, ADAE, these were just reflection about angle bisector. So you get that it has to be that involution. So you get that the third one also has to be reflection about angle bisector. So you get AF and AG are isogonal in angle BAC. Okay, like just this is very trivial, but still. So how many involutions, if you get, will you have a special case? I mean, a special case, I mean, so like concurrency of three lines is a special case. I mean, it doesn't always occur. Or collinearity of 3 points is a special case. Consecutivity of 4 points is a special thing. So what is a special thing for number of like involution pairs?
3.
Yes, three is correct. So if you get three things like A comma B, E comma D, and E comma F, this would imply that I mean this is a special thing. If you get this, it's non-trivial. Because A comma B and C comma D is always trivial because there will always exist some involution. But if you add E comma after that, it's non-trivial. Okay, this was what was about. We will now switch to DIT. I mean, not switch, we'll proceed to DIT. But DIT is Desargues involution theorem. Okay, so we first have a complete quadrilateral sort of. And then you pick any other line L, which does not, okay, so these are the vertices. I'll name them. So now you pick any other line L which does not pass through any of these vertices. Okay, I should draw. What should I draw? Yeah, and now on this line you mark intersections. Yeah, so these are the intersections. I will name them. What is this? So if this is the line L, what you have is that x1 comma x2, y1 comma y2, and z1 comma z2 are involution pairs. So how I have chosen this is line L intersects AD and BC, so those are like opposite two sides. AB and CD, these are these 2 points, and AC and BD. So since this is a complete quadrilateral, we really don't care about which are the diagonals and which are the sides. So it intersects like opposite sides, the intersection of opposite sides with L on involution pair. And the interesting thing is that if you have any circumconic through this thing, through A, B, C, and D, any circumconic you have here, and if you mark the intersection of line L with the circumconic, let's say W1 and W2, then W1 and W2 are also involution pairs. So the intersection of with opposite sides, you get three such pairs, and the circumconic, you get one such pair. All of these are involution pairs for some involution on line n. Does that make sense what the statement says?
Yes.
Okay, so is this clear to everyone or should I repeat again? You can take any such circumconic and it will still form an involution pair with that thing. Also, thing to note is that L does not pass through A, B, C, or D. A can indeed pass through these points though, like the intersection of diagonals, but it should not pass through the vertices. Is this okay? Okay, so one interesting thing that we note here is that usually when we get special things like let's say concurrency of altitudes, let's say, what you get is that three lines concur. And this is the minimal special thing, right? Because two line concur, we always know three lines concur is special. So you get that these three lines concur. But here, if you observe in this theorem, you have four involution pairs, while three was special. So this is like a very strong theorem because even three are special, and you actually get four involution pairs. So this is like really strong. Does that make sense?
Yes.
Okay, next. So there are some degenerate cases of DIT, like we have the 3-point DIT. So what you have some circumconic. And you draw a random line L. Then these are the points.
The line through A is just a line or is it a tangent?
It's the tangent. These are the tangent. So you get that this one. These are the involution parts. Does that make sense? Basically, you just like took T as A. Is this fine?
Yes.
Oh, so similarly, you have the 2-point. Oh, sorry, yeah. Similarly, you have a 2-point DIT. So if you have conic, this is the tangent. And if you have any other line L, and these points x1, x2, w1, w2, and you would find this thing z. So you get that x1 comma x2, w1 comma w2, and z comma z. Note that you get the repeated thing here. These are involution pairs. You just showed the you just took A is same as D and B same as C here. Does that make sense?
Yes.
Are x1 and x2 the intersections of the line with the tangent?
Yeah, it's this point and this point. And W1 is the circle intersection with cone A. Z1 is the intersection with line AB. Also, like just a reminder, since we are working in the projective plane, if even if the lines are parallel, they have an intersection at point and infinity. So these intersections are always defined.
Wait,
Okay,
so
these are
it's
yeah. Go on.
yes. Is it A goes to A and B goes to B, or A goes to B and B goes to A?
Sorry, what do you mean?
Is it A goes to B and B goes to A, or A goes to A and A goes to and B goes to B, and B goes to B in
No,
this
these are
case?
involution pairs on line L, not on conic C.
Oh, okay.
Because all these points lie on the line L, right?
Yes.
So these are involution points on line L. And line L never passes through A and B.
Okay, wait. No, but then what is the then which involution are we taking the pairs on?
Sorry?
Then which involution are we taking the pairs on?
No, when I say that these are involution pairs, what I mean is that there exists some function f or some involution f on L whose involution pairs are these.
Oh, okay. Thank you.
Wait, so Z will be kind of the center of involution, right? Here. So like Z will be the center of inversion or the
Not the center of
reflection.
inversion exactly, because center of inversion will be mapped to the point at infinity.
Yes.
It
Oh,
will
wait. Oh, correct, correct.
it will be the what do you call, like the circle intersection of circle with the line, or it is the if this inversion is the reflection, it will be like, if you line this line, if it's a reflection, it will be reflection about Z, and if it's a
It's a inversion, it will
inversion, it
be
will be like one of these points.
okay.
Assuming it's a positive inversion, if it's negative inversion, I don't think any point gets preserved. Okay, so these are the degenerate cases, 3-point DIT and 2-point DIT, and this is the Desargues. The proof of this is like pretty easy. I mean, you just have to project from few things for few times. You can do that later. Okay, so now we shall proceed to DDIT. Okay, why am I writing? So DDIT is basically dual of Desargues of DIT. So I believe you know some projective duals thing. So can anyone try to state what DIT should mean based on what Desargues we did? I will give you some 5 minutes to do that. Okay, maybe I will like paste the DIT ka photo, DIT ka diagram here so that it will be easier for to write that too.
I'm sorry, I just missed what was happening for the past few seconds. Could you just repeat?
Yes, did you understand the concluding part of DIT? Like this,
Oh, yes.
you understood the Z combination, right? Okay.
Yes, yes.
So now we are trying to state dual of Desargues involution theorem. So observe that DIT is purely projective, right? It
Correct.
just takes care about intersections and things. So we can write the dual of it. Like dual is a projective dual. So this is the Desargues which we wrote above. So can you try to write the dual of DIT? That is the DDIT, the DDIT theorem.
So in the dual thing, the reciprocal pairs will be the lines.
Yes, exactly. Reciprocal pairs will be the. Hello, can you hear me?
Yes.
Okay, yeah. So reciprocal pairs will be the lines. That is true. And here, since we have a variable line L, you will have a variable point P.
It's a polar duality, right?
Yeah, exactly. So you take duals with respect to conic C, and then you restate DDIT.
See, the conic becomes another conic, the quadrilateral becomes, it's like A, B, C, D become lines and their corresponding sides become points. And then
Yeah, exactly. So like, can you state that?
it will be almost, it'll be very similar, right? Like,
It will be a bit different, not exactly similar. Like some part of the figure will get.
because L will be a point and then the sides are just points. So like the intersection just become lines. So like it's sort of similar.
Yeah, it is similar because it's the complete quadrilateral, so it has to be, you know,
Can you just
sort of
state the explicit version?
what? Sorry.
Can you just state it explicitly?
Yeah, I mean that's what I have. Like that's what I think people are trying.
Oh, okay.
So if anyone has any idea about statement of this explicitly, can just say.
Okay, so you take A, B, C, D as points on the plane, and
Let me draw. Yeah, so you take. Yeah, go on.
you take another point P, and then you complete the quadrilateral of A, B, C, D with AB cap CD, AD cap BC.
I should shift the point here as well. I will shift the figure down. Just a minute. I'll redraw. This is what you mean?
Yeah.
Yeah, you have point P.
Now you take some point P and you take a conic tangent to ABCD and in one of its inconics.
How do you draw the
And now you draw the tangent from P to the conic. So those two tangency points are G and H. So PG, PH. So we take the pencil lines passing through P, and we'll get it. I think we'll get an involution on that. One is PG, PH, and then I think we'll have PA, PC, PB, PD, and PE, PF.
Exactly. Correct. So what you have is you have a quadrilateral ABCD. Important thing to note here is that we are not completing the entire quadrilateral. Here the order of points matter. Like here we actually care about what the diagonals are. So here we have AC and BD as diagonals. So what you have is PA comma PC. These are the opposite vertices. PB comma PD opposite vertices, and then you take the intersection of sides P, E, and F. So P and PS. These are involution pairs. And if you have any inconic to ABCD, the tangents of P will also be part of the involution. So restriction on P is that P can't lie on any sides. It can lie on the diagonals, but it can't lie on sides.
Can it lie on
Uh,
the conic?
sorry,
Can it lie on the conic?
it can lie on the conic, yes. Conic is basically variable, and you can just like vary the inconic. Important thing to note is that what we usually take as diagonals, you might not take this as diagonals always. Like if you here in the above figure, if you have something like this, okay, I should draw better. Yeah, if you have A, B, C, D, what we usually mean by diagonals is AC and BD. But here you might take AB and CD as diagonals. Then your quadrilateral will become ACBD. This will become your new quadrilateral. So your inconic has to be tangent to AC, CB, BD, and DA. And your opposite vertices will become A comma B, C comma D, and the intersections that you should take are you should exclude the intersection of diagonals. So AB cap CD, this intersection you will neglect here and take these two intersections. Does that make sense? Give me a minute. Okay, so does that make sense that why diagonals can also be not diagonals but sides?
Yes.
Yeah, okay. So this thing is also important to note that the inquiry should be tended to the sides and not diagonals. So maybe you have something like this line AC, this line BT, this and this. So you can have an inconic something like this. So also a thing to note is that inconic might not always be an inconic, it can also be an exconic. Just the thing is that this all the sides should be tangent to it. Does that make sense?
Can it be a hyperbola instead of an ellipse?
Yeah, yeah. I mean, it's conic, so it can be literally anything. I just draw ellipse because it's like easy to draw. Usually we will be dealing with circles, but you can also have ellipses and hyperbola. No problems. Okay, so we now have the degenerate cases like the 3-point DI, 3-point DDIT. So here you will get that PA comma PD, PB comma PC, and PG comma PH are involution pairs. Basically, you end D such that B comma D comma C are polynomial. Does that make sense? If you observe 3-point DDIT will be the dual of 3-point DIT. So that is basically the same. Okay, wait, is it? It's not.
Is this
What
a
is it?
degenerate case of 4-point DDIT?
Sorry?
Is this a degenerate case of 4-point DDIT?
Yeah, exactly. This is a degenerate case of 4-point DDIT.
And is it the dual of 3-point DIT?
Yeah, I guess so. I have not checked myself, but it should be. That is 3-point DIT. Okay. So this line will goes to point. Is it really? I'm not sure. What do you think? L will go to this. Tangent will go to this point. A will go to a tangent. Yeah, it is. It is the one. That is correct. Okay, is it? Yeah, it's the dual. That is correct. It is indeed the dual of 3-point DIT. I mean, it should be basically because 3-point DIT is degenerate of 4-point DIT, and 3-point DIT is degenerate of 4-point DIT. So is this clear? PG and PH are tangents. Is this okay?
Yes.
Okay. So we also have, like, as you might have guessed, we also have 2-point DDIT. Just one thing to note here is that sometimes this circle can also be the X circle. Like this is in triangle ABC, this is the in circle, right? But it is sometimes also beneficial to have the X circle, as we will see in some problems. So 2-point DDIT. 2-point DDIT, you can state it this way of some conic. 2 points here, okay, this here. Then you have these are involution pairs. And note that just like in 2-point DIT, we got Z comma Z as the repeated thing. Here we have PT comma PT as the repeated. So this is one thing to note. This is the 2-point DDIT. Okay, is DIT, DDIT, all the forms of DIT, DDIT clear to everyone?
So all these are involution pairs of a pencil.
Yeah, these are involution pairs on pencil. These are involution pairs on pencil of lines through P.
Okay, got it. Yes.
Okay, so one thing to note is that for the 4-point DIT and DDIT, we got 4 involution pairs. But for 3 and 2, one thing gets repeated, so you get 3 involution pairs. Even 3 is special case, of course, that we observe because 2 of them uniquely determine one thing. Okay, so this is the theory part. We will now get down to some applications or like problems or like how to use these things. First thing that it's well known, like isogonality lemma, like 1 or 2, I don't remember exactly, but something like that. So what we have is in triangle ABC, points P and Q are there. So what you have is if AP and AQ are isogonal, then if you have like BQ cap CP equal to R, BP cap CR, sorry, CQ is equal to S, then AR and AH are also orthogonal.
I think this is second isogonality lemma.
Okay, okay. Yeah, orthogonal lemma two. The first is the reflection about midpoint or something. Okay, I'll give you 5 minutes to try this.
I think I know how we could go. Like, I'm thinking that if we could use DDIT on quadrilateral PQSR, we know that APAQ and ABAC, if you have if you make our involution the reflection across the angle bisector of BAC on the pencil of lines passing through A, you're given that AP and AQ are involutory pairs and AB and AC are involutory pairs, and we want to show that AS and AR are involutory pairs. So I'm thinking DDIT and PQRS would be useful over here, something on those lines.
Yes, exactly. That is correct. So we uh, apply DDIT. Sorry. Yeah, we apply what is this? Yeah, apply DDIT to just not PQRS. We write like PRQS because here we want PR and PR to be the side and not we want like PQ and RS to be diagonals. So with respect to point A, or basically like you can also say that this is in quadrilateral B P C Q with respect to A. That's basically we get the same thing. So what we'll have is AB comma AC, AP comma AQ, and AR comma AS are involution pairs with respect to pencil of lines passing through A.
Right, and AB and AC and AP and AQ are reflection across the angle bisector, so then we get that AR and AS are isogonal.
Yes, exactly. These are reflection about angle bisector, so you get that AR and AS are isogonal. Did everyone get this?
Yes.
Okay. So did, do you mind if we go a bit overboard because we are short on time? So I might have to extend it a bit. Let's see. Let's do at least one problem. We'll decide about the other one later. Okay, I'll just copy it. Okay, so this is the problem. This doesn't require DIT, DDIT as such. It can also be done using cross ratios only, but I like to present it in terms of involutions. So we can present the involution solution here. You guys can try this for 7 minutes, 5 minutes. I'll draw the diagram by then. Okay, anyone has any ideas of what we can do?
I was thinking of DIT on DTFG or wait, DTPG.
Okay, TTPG. The thing is, if you even if you apply DIT, only one point is known. Like PD intersection TG is the only intersection that is good. Otherwise, PG intersection DT is not known. GT intersection PT is also not known.
Correct. That's what I was trying.
Okay, so I'll just start if anyone has ideas we can share. So we don't really require DIT, DIT here. This can be framed in terms of involutions. So what point do you think that I should mark in the figure that would make it more complete? Like, which is the most intuitive point that you think I should mark in the figure?
The midpoint of BC.
Exactly. So why this? Because
Because one thing is that, and also the condition that three frames are showing AQ cap BC, we have this harmonic.
yeah, exactly. We have the harmonic thing because AQ parallel to BC, and we also have the M as the midpoint of BC and DT. So
Wait, what do we have
one thing,
harmonic?
like you have, if M is the midpoint, then you have BC, M infinity.
Infinity, okay. Yeah.
Yeah. Similarly, you also have DT, M infinity. Okay, so one more thing, for one more point I will mark is that M dash is equal to AM cap circumcircle of APG. Why this point? Because if you observe D ka image you have, D ka image you have, T ka image you have, F ka image you have. Sorry, I mean C ka image you have. So you can basically project this line onto the circle now and think. So that would make it easier.
Wait, can you just repeat what he said? Wait, also E and F lie on APG, right?
E and F lie on APG, yes. That is why, because you can now project this line onto the circle completely through A. Does that make sense?
No, wait, no, I didn't quite get it.
Okay, yeah. So why does it make sense to introduce this point is that, so if you see the points on line BC, what points that are relevant in point BC on line BC? B, T, M, T, C, and infinity, right? These are the relevant points that we have on line BC.
Yeah,
If you project this from A, you get E, you get
onto, wait, but it will be projecting on APG, right?
yeah on APG. So you get P.
E,
Here you don't have anything right now. Then you get G, F, and here you will get something later. So you get that these are the involution pairs, right?
yeah,
I mean these are the points. So it is good to define M dash because you can now complete this figure.
yeah.
So so basically recently what we had was B comma C, D comma T, and M comma M are involution pairs because it's just reflection about M. So if you now project this on the APG circle, what we will get is that E comma F, D comma T goes to P comma G, no, yeah, P comma G and M dash are the involution pairs. So that essentially means that QM dash is tangent to APG.
Wait, does Q lie on EF and
Q is
what?
defined as EF cap PG.
Oh, okay.
So QM dash will be tangent to the circle. And one more thing to observe is that here you have this is equal to -1, or maybe this is equal to minus whatever. So if you project from A, you will also get that uh, okay,
E
so
and
what
M.
thing do you think we need to prove now? So one point we are not sure about what right now is A infinity intersection APG, right? A infinity along BC, yeah, APG. This point we are not sure about right now. What point is this? So we can even just guess and prove what point is this.
Is it A itself?
Yeah, exactly. So it's A. So basically, we are claiming that the tangent to at A to circle APG is the line parallel to BC. It's just trivial angle here because this angle is same as this angle is same as this angle because PGMD is cyclic.
Wait,
PGTD
can
is cyclic. Yeah, sure. So consider the tangent to circle APG at A. Like let this be the tangent. Then this angle PA and that tangent angle is equal to PGA by tangent C, whatever the tangent C angle thing. And now this quadrilateral is cyclic PGTD.
Oh,
So that is same as this angle. So it's parallel to BC.
okay.
So now you have that A infinity BC intersection APG is parallel to BC. So you have here by projecting this thing on APG, you get that what is this? PG AM dash is equal to -1. So that quadrilateral is harmonic, right? So you have that PG M dash A is equal to -1. It is harmonic, and QM dash so Q is equal to PG cap
But then
MM dash M dash M dash. Yeah.
wasn't it basically done, right?
Yeah. So QA is tangent to
Yeah. But then
APG.
that,
That
but
basically
since
means AQ parallel to BC.
yeah.
Did everyone get the proof? Should I repeat anything?
Wait, you got PG comma M dash A is equal to -1. Then how do you proceed?
Yeah, so we got that. We know that QM dash is tangent to APG, right? At M
Correct.
dash.
Yes.
So what you basically have is that you have this circle A M dash. This is Q, right? Q and this is a harmonic quadrilateral. This is a harmonic quadrilateral by that thing. So intersection
Yes.
of tangents at opposite
Oh
vertices
wait.
lie on the side.
Oh yes, correct.
Okay, so we are like already over time, so I will stop now. I had some more problems, but I will share them with you later.
Will you put them in the preset?
Yeah, sure.
Okay.
Okay, I'll stop sharing. Does anyone have any doubts?
Can you suggest a nice handout for involution?
Yes, so I think Mark PCC has a nice handout. Also, the ZG nuclear Erickson's handout is good. I think I had one more handout. I will just search for it and share.
Okay, thank you.
Okay, if there are no doubts, I will stop recording.